All right, welcome, folks. As people are trickling in, just want to have a warm welcome to this manufacturer's roundtable on high performance windows. We have a great panel set up today to talk about some of the best window offerings on the market, as well as some research into the most efficient windows kind of possible, and as well as some even energy producing windows. So we have a lot of exciting things to talk about today. Before we get into it, though, I want to pass the mic over to Sean Williams from the California Energy Design Assistance Program. CETA is our sponsor for today's webinar. So with that, Sean, you can just tell me next slide and we'll let you talk about CETA.
Awesome. Thank you for the handoff and you all allowing me a few moments here to chat about the CETA program, also known as the California Energy Design Assistance Program. So CETA, what is CETA? It's the only statewide utility-sponsored incentive program for new construction and major renovation projects that are in the design stages. The purpose of the program is to promote electrification as well as decarbonization. CETA does work in collaboration with project teams to reduce energy demand, consumption, as well as carbon emissions. Through the program, we do accept and serve commercial, public, high-rise multifamily, industrial, and agricultural projects that are located within Pacific Gas and Electric, Southern California Edison, SoCal Gas, and or San Diego Gas and Electric service areas. Next slide for me. And through the program, we do provide incentives through for those new construction and major renovation projects for implementing energy efficiency measures. So two types of incentives I just want to touch on real quick here. We do offer a $4,000 design team participation incentive. And it's per project and goes to the project team for enrolling as a thank you for participation. And then we also offer what we call a measure package incentive. And this goes to the building owner, your client. And it is based on the project measure package that the design team would choose to implement. Next slide for me. And why participate in CETA? $1 million question, but a couple key points here. First, you will receive a custom and complementary decarbonization analysis that's tailored to specific project goals and with hopes to help in identify the most effective energy efficiency measures to implement for your project. Great way to gain analysis of energy cost and paybacks. And of course, receive financial incentives to help offset the cost of those decarbonization measures. Last but not least, demonstrate a commitment to high performance building practices and design. Next slide, please. So just briefly touching on some of the high performance measures that we do look at through the program. We do aim to exceed California's decarbonization standards by identifying high performance measures and providing educational opportunities to explore use cases and best practices. This not only advances the market, but also qualifies participants through enhanced incentives. We do have on our website a current list of eligible high performance measures, and you can just find that at CETA.com. Excuse me. Next slide, please. And right here is my contact information. I got my email there. So if you have any current new construction or major renovation projects in design, feel free to reach out. I just want to highlight that the program is pre-funded and it's 100% complimentary and really only takes about 2 hours worth of participation time. So the incentives are available and we are still allocating those incentives to projects. So would love to chat with anybody if they have any projects and, see what level of incentive we could allocate to those types of projects. Thank you all.
Thanks a ton, Sean. Appreciate it.
Thank you.
Sweet. So on to the main subject of our webinar today. It is high performance windows. So why are we discussing windows? Well, in today's webinar, we'll discuss how they have a very pivotal role in a building's energy profile. Windows are often the weakest link in your building envelope. So strengthening them, basically increasing their R value or their ability to either keep heat out or in, is really critical for a high performance building. So they're directly going to affect heating, cooling, ventilation, and lighting demand. So there's a whole lot of building science that goes into it, and they can make a massive difference on your energy draw in a building. And some examples of modern day solutions that we'll discuss today are things like triple pane glazing, innovative frame materials, and smart window tech, such as solar generation. We'll also hit on some market adoption challenges. We'll discuss some costs, which are often not going to be nearly as bad as some folks make them out to be. We'll talk about a path towards integrating fenestration in things like passive house or ultra high standard building, as well as some other high standards like passive house. And with that, let's talk about who our presenters are today. It's a great lineup. I will let them introduce themselves later, but we have Lisa from Geldwin, Ali from Alpin, Katie from P&L, and Lance from NREL. So we're kind of starting with a couple of available products on the market today, a bit of an overview or a, high performance Windows 101, and then we'll dive into some lab research and some advanced technology like solar generation within Windows. So with that, I'm going to stop sharing, hand it over to Lisa, and let her discuss some of the Gel1 products.
Thank you. Thank you, Noah. Let me just share now my screen. And screen, there we go. Share. And so just there we go. So thank you for having me. My name is Lisa Bergeron. I'm with Geldwin of Canada. I've been with Geldwin for over 36 years. I'm the Director of Business Development and Regulatory Affairs. I work with my role is really to work with governments and also association, and I lead a development group in Canada. So today I'm going to talk about the impact of high performance fenestration on the building envelope and how there's a window of opportunity. So what you need to know about windows is essentially they are, as Noah pointed out, they are the weakest component, but they're also the largest or the biggest opportunity with the fastest payback for builders. And that windows have the biggest impact on cooling loads. That's very important. So one thing that we've been working on at Geldwin in Canada is changing the narrative from first cost to total costs. So our journey started in 2015. We had meetings. I was having a meeting with UL, and a gentleman was telling me that we needed to start figuring out how to make better windows because it was really the biggest opportunity on the building envelope. And so started talking to me about the effective R value and how windows are much better or have a bigger impact on the effective R value. So, and this is really easy to, like a simple way to show this is if you have 50% fenestration, 50% wall, and your fenestration is at R2 and your wall is at R20, you have an effective R value of 3.6. But if you double your insulation, so you go to an R40, your bang for your buck on your effective R value is minimal, marginal. But if you doubled the bigger bang for your buck. So essentially, windows are the clear opportunity. Just get to and so we set out to work with one of our partners, Building Knowledge Canada, who's a whole house building envelope modeler. And we wanted to know what, how the window to wall ratio impacted the overall effectiveness of the wall. Or, and how, were there benefits for builders to move to a better window, and were there any homeowner benefits? So we did 1,200 whole house energy models in zones 5, 6, and 7. And we modeled different window to wall ratios against different wall configurations. So we had an Energy Star wall, a net zero wall, and what we called a prairie wall. That was that we were comparing, and we had window to wall ratios from 5% to 50%. So we did a pretty extensive change. Whoops, I went too fast. And so the conclusion of this our study was that at 13% window to wall ratio, you're better off to consider putting in a tri-pane or better window than putting in 1 inch of foam. It actually raises the effective R value of the entire envelope. And so it's not about necessarily trading off insulation against windows, but if you're at the stage where you need to make decisions, if you're doing a net zero, you're of course you're going to be forced into putting in or passive house, you're going to be forced to be putting in at some point some exterior insulation. But if you're just trying to get to a better number, windows actually are a bigger bang for your buck at above 13% window to wall ratio for 1 inch of foam. And once you get to 20% window to wall ratio, windows outperform, if you will, 10 or R10 or 2 inches of foam. The benefits for builders were that trading off, one of the benefits we determined was that there was a diminished cooling load of 1,300 or 13,000 BTUs, which means about a reduction of a ton, which is quite significant in a dollar value. And there was really no learning curve other than it is less labor than adding exterior foam. And there was reduced callbacks, less risk of condensation. For consumers, it was essentially healthier homes, quieter homes, and essentially no short cycling of oversized mechanicals. Because if your mechanicals are not properly sized, then you become uncomfortable in certain areas of the house, or you can anyways. So in 2023, we decided to redesign our casement fixed awning products because the government of Canada had put out that they wanted all windows in Canada to be at a minimum of 0.14 U value by 2030. We were also trying to get this done without any, just using regular technology. We wanted to design a window that would meet the 0.14 U value without using, extra, anything other than argon and just regular tri-panes. And that was because we felt that affordability was very important if we were to go down that route, and that we could eventually, with those window systems, when technology was on point further down the line, we could always incorporate it into this system. So we went back to building knowledge and wanted to know this time, how did the new window stack up against better walls, but also airtightness, because airtightness is really easy. It's a inexpensive, so I want to say most cost efficient way of improving your building envelope, but it's also the hardest because you're relying on trades most of the time. So we wanted to find that out, and then we wanted to know how the new window stacked up against other measures on operational carbon, and also how did it reduce cooling loads in zones 2, 3, and 4, as we had done previously, 5, 6, and 7. So we chose Dallas, Phoenix, and Seattle on a 2,600 square foot single detached, the gentleman window versus 2 air changes of air tightness. Sorry, R5 continuous insulation, R7.5, so 1.5 inch of foam. And then an R10 for Seattle, because I believe that in Seattle, I think they already require 1 inch of foam. And we used 12, 17, and 22% window to wall ratios as a standard. So what we found was that for Seattle, only the R10 on an operational carbon did perform better than the Jeld-Wen window. From an energy consumption, the Jeld-Wen window performed better than all other measures. Then in Dallas, the Jeld-Wen window outperformed all measures on both the operational carbon and the energy consumption. And the same thing in Phoenix. One of the things we did was take a look at what it did to the cooling loads and what the new window did to the cooling loads in those markets. And so essentially in Seattle, there was a reduction of 1 ton for the air source heat pump and a significant reduction in duct size, so from 24 by 10 to 22 by 8, which essentially means smaller bulkheads, more space. In Seattle, we were comparing to the IECC 2021, and I believe in the other 2 markets, we were against the IECC 2018. Maybe not. They were comparing 2021 in Dallas as well. Sorry. So in Dallas, it was 0.5 ton of savings and a little reduction in the duct size. And then in Phoenix, Phoenix was, sorry, the 2018 IECC. And in Phoenix, we also saw a reduction of 1 ton on the air source heat pump. So the conclusion was that for Phoenix and Dallas, at all window to wall ratios, both from an operational carbon and energy savings, the new Jeld-Wen window was better than all the other upgrades considered. For Phoenix, for Seattle, at all window to wall ratios, on an energy savings, the new Jeld-Wen window was better. But in Seattle, at less than 13% window to wall ratio, the R10 insulation performed better on the carbon emissions, but above 13%, the Jeld-Wen window performed better as well. And then for all climate zones, a reduction in mechanical sizes and duct sizes was observed. So one thing we also wanted to, we talk about energy efficiency and the cost of going to a new tri-pane window. And the one thing we wanted just to talk about generally is that energy efficiency is not a function of design. So if you're comparing just a white vinyl window, plain Jane, no bells and whistles, then the upgrade can be significant, from on a house package. We did this 2,600 square foot house package. This is what this is based on. But then when you start adding, color, which is quite prominent, and then you add wider jambs, brick molds, hybrids, which is an aluminum cladding that we do, you can see that the increase for upgrade diminishes significantly. So, and for us, the energy efficiency, the cheapest form of energy is the energy saved. So investing in a better window makes a lot of sense for builders and for homeowners. So I just, in closing, would like to run a little video. Let me just see.
Geldwin, changing the world of windows. Geldwin's cutting-edge technology introduces the sleek, innovative JWC 8500 window, the first of its kind, where energy efficiency meets design flexibility. Geldwin has developed this window to meet future codes that stand the test of time. Vinyl at its core, with the option for a clad interior or a wood interior, an aluminum exterior, featuring a dual pane option, as well as our true tri-pane technology, outperforming standard tri-pane windows by 30% in insulation. Our revolutionary hardware offers a sleek, low-profile design for any window style. With an increase of 26% in glass area, this window achieves state-of-the-art performance with a vinyl core and the versatility of its design elements. Geldwin, changing the world of windows.
So,
Geldwin.
no, sorry. So that's all I had. I want to thank NBI for asking me. Our products are available, even the Canadian products are available across North America. So feel free, that's my info there. Feel free to reach out if you have any questions.
Lisa, thanks a million. That was great. Really appreciate it. And we do have a question, but I'm going to save all the questions for the end after folks have gone. But yeah, if anyone has more questions for Lisa or any of the presenters afterwards, please use the Q&A feature rather than the chat, just to keep everything organized, and kindly say also which presentation you're directing the question at. But again, we'll hit the Q&A at the end. Thanks again, Lisa.
You're welcome. Thank you.
All right, Allie, you want to jump in?
Sure. There we go.
Looks
So
good.
we're on, yeah. So yeah, my name is Allie. I'm with Alpin Windows. I'm the director of new product development here. And although we love to stay at the forefront of new and innovative technology, today I'd like to talk a little bit about keeping it simple and how we can improve window performance in very low cost and simple ways. So our mission at Alpin is to affect the built environment by achieving 3 sustainability imperatives, which are decreasing heating and cooling emissions from buildings, reducing the carbon intensity of the traditional building materials used within them, and enhancing the operating economics, which means the cost of heating and cooling your buildings. And so we recognize there's plenty of sexy innovation for the new construction market. We have electrochromics, photovoltaics, daylight redirecting, vacuum insulating glass, and other phase-changing technologies. But what are the simple technologies that we can look to? And so what do we do about the windows that we already have in the built environment? Sorry, I'm going to switch over to here. Most of the world's building stock is already built. The US has 5.5 million commercial buildings. Nearly 30% of those still rely on single pane windows. And that adds up to about 2.6 billion square feet of single pane glass. And in the window frame market, most of the window frames in the US were optimized for double pane glass. And that was the standard of advanced glass for a long time. And NFRC thermal modeling dictated that a half-inch argon gap is the best performance. So window frames today just aren't equipped to handle, what kinds of advanced glass that we are producing now, like triple and quad pane. So the result is that we have millions of windows that physically can't accept higher performing glass. Sorry, I've got to switch back over. So the implications of this is that full window replacement is expensive, it's disruptive, it's carbon intensive. So replacing all of the windows in our existing building stock is not feasible. And the existing window frames, many of which require substantial alteration, or else they must be used with traditional kind of lower performing double pane glass, which blocks the amount of energy savings and decarbonization potential. So the real challenge is, how do we unlock high performance window retrofits without having to substantially alter our window frames or completely rip them out of buildings? So the opportunity that we will talk about today is simple innovations like thin glass, IGUs, and Winsert. So keeping it simple, thin glass. Thin glass is widely used and it's proven. It is used in solar panels, smartphones, and flat screen televisions. Most people with an iPhone, if you tap the screen, that is a thin glass product. As a result of this rapid adoption in the global market, we're seeing a rise in ultra thin glass production. From today, it's about $16 billion industry, and it's projected to grow to $35 billion by 2034. So this rapid growth means that we have an expansion in capacity. And so this strong, flexible product, now available at the global scale, makes it feasible to use thin glass in architectural applications. So what is thin glass? Thin glass is 0.5 millimeters to 1.3 millimeters thick. I will play this. It is lighter weight than traditional glass because it is about 3 to 4 times thinner than typical residential glass and 6 to 8 times thinner than typical commercial glass. We can take a 1/4 inch commercial unit, which is 3 pounds per square foot, and cut that weight down to about 1/2 pound per square foot. The strength of the product really comes through the amount of its flexibility, that it truly bends. So the video that I will replay, so this is a video where we took a 50 square foot unit that's a quad thin glass. So 2 panes of 1/4 inch glass, 2 middle panes of thin glass, and we subjected that unit to 240 mile-an-hour wind speed. And we've carefully monitored the deflection of those 2 inner thin layers. And we were surprised to see that when it reached its final breaking point, it was actually the 2 panes of 1/4 inch glass that broke first and then shattered through the thin glass layer. So it's very capable of meeting the design loads of the built environment. Thin glass is also less energy intensive and has lower embodied energy than traditional glass by virtue of how many sheets of glass that we can produce out of a single ton. So a traditional float line uses about 9.3 million BTUs of energy per ton that it is manufactured. 1 ton of, say, 1/8 inch residential glass can produce about 1,225 square feet. With that same ton of glass at 9.3 million BTUs, we can produce over 5,000 square feet of thin glass. So once we amortize that, the energy usage across the how many sheets of glass that we can produce, we're dropping our GWT, or global warming potential, per square foot of glass, that we're cutting that in half or more. So the result is that with thin glass, we can make lighter, lower carbon insulated glass units that both fit retrofit and new construction. So applications of thin glass, we have been using them as the center layers of triple and quad pane glass units since 2018. Use of a thin glass triple instead of a double pane in a conventional, say, vinyl window. It will net a center of glass U factor reduction from 0.19 to 0.11. And in the whole window, this is a vinyl double pane, kind of generic. We've resulted in a 0.25 U factor, dropping down to that Energy Star most efficient category of an R5. And so we can integrate these in both thin, narrow pockets or wider glass pockets. When we get into the quads, of course, the more space we can have, the better performance we can achieve. But on top of just retrofitting narrow insulated glass pocket frames, we've also started innovating on retrofit solutions like Winsert. Windsert is a secondary window product that is very lightweight. It's using that thin glass, about 1/2 pound per square foot, in a very simple fiberglass frame. So this means that it's a lightweight, easy to deploy product that has very fast installation. So we did a project in Vancouver with 6,000 square feet of windows, and it only took us about 4 days, and most of that work was done at night. So we just had to ask folks to clean off their windowsills, and we could just slide the windserts in, and they come back to a fully retrofitted window. The thermal performance is significantly improved. Existing window, say a single pane aluminum window, has a U factor about 1.1. If we put a simple Windsert light, a single pane of thin glass in a fiberglass frame behind that window, we cut the U factor in half. And then if we do a double pane Windsert, we call it the Windsert Plus. So it's a piece of thin glass and a piece of 1/8 inch thick low E coated glass. We cut that U factor in half again. So we've taken an R1 existing window all the way to an R5.6 just by use of the Windsert Plus. The core advantage and the unique part about it, what I get excited about in this product, is that we're using that fiberglass frame and we are covering over the existing frame, so we can isolate the effects of both the single pane of glass and the aluminum frame to substantially improve the edge of frame performance and that comfort that results from it. So it's a completely new product category. It's an exterior storm window. It's not a window replacement. We're not applying a film. We're not just treating the gaskets. We're actually addressing all of the energy and comfort problems of an existing single pane window. So we're insulating the existing frame to reduce heat loss and cooling loss. We're helping to lock up any leaks or drafts that might be in that existing frame. And we're achieving that with a very low installation cost, low weight, rapid deployment, and minimal disruption to the building. This product is third-party tested. The AERC, the Attachment Energy Rating Council, has certified the Windsert Light and the Windsert Plus to achieve thermal performances of that R4.9 to R6.3, the U factor 0.10. And they do these ratings based on a generic window frame. So they take all secondary window products and they measure the thermal performance improvements on the same baseline frame. Additionally, the Windsert energy savings capabilities were studied and validated as part of the GSA Green Proving Ground project. In it, they installed Windserts into 2 buildings within the Denver Federal Center, and they measured the temperature, the surface temperatures of the glass and the changes of temperature inside the room to validate that the real world performance matches with the therm modeling and window modeled performances. And with that data, they can then take, they validated that the therm and Windows 7.8 models were accurate, and they plugged that into a Energy Plus whole building energy model for several federal buildings in different climate zones throughout the US. And they calculated what the energy savings potential could be if the whole building was retrofitted with Windsert products. And the average predicted whole building energy savings was about 15%, with a payback of 8.4 years or less in some cases, some climate zones. So on top of the energy savings, we've also have some real world anecdotes of the comfort improvements of the Windsert product. So in Vancouver, again, the building owner reported that most days when the temperature outside was 95 to 100 degrees, they would actually let the employees go home because it was too warm inside the offices to stay working. It was about 90 degrees inside. But after the Windsert product, they actually had a day where the outside temperature hit 115 degrees. And that same office, the 4th floor, they were all very comfortable. They maintained a temperature set point of 72 degrees. So confirming the comfort impact of Windserts. So in that building, we also set up a small study where we had a space heater during the winter days, and behind a Windsort Light and a Windsort Plus, we just monitored how many times the space heater kicked on a cold winter day, and just measured the amount of kilowatt usage behind each of the two. And so we did find a 38% reduction in space heating behind the Windsort Light and a 45% reduction in space heating behind the Windsort Plus. Nope, sorry, wrong way. So another benefit to the Windsort is it is aesthetically invisible. It does sit behind that existing window frame. So we're able to deploy this product behind historic windows without changing the visual effects of them. So this is that Hills Plaza in San Francisco, California. We installed Windsort lights throughout the entire building, and we saw a significant improvement in the HVAC system's ability to maintain consistent temperatures. So this is a small scattering of some of the Windsort projects that we have out in the marketplace. And we are gaining new opportunities to deploy Windsorts on a daily basis. So if you do have any questions or follow-up about the Windsort product or about our thin glass, we invite you to contact Pierre or myself. Thank you.
Thanks a ton, Ali. That was awesome, and love seeing the like temperature fluctuation charts and how easy the retrofits are, and real life savings. So all really great info. And yeah, again, if folks have questions, please feel free to direct them to Ali, and we can address those after the fourth presenter goes. But yeah, thanks again. Awesome, Katie, you're on it. Thanks so much.
I think, oh, I haven't gone to presenter mode. There we go. Okay.
Great.
So my name is Katie Allen Court. I'm a research economist and project manager with Pacific Northwest National Laboratory, which is one of the Department of Energy laboratories. We're located out in Eastern Washington State, and that has been my home for the last 27 years. So I'm going to be talking to you about some of the residential research that we have done with, sorry, I'm having trouble seeing in my slides. Okay, so I'm going to be highlighting some of the field validation work that we've been doing at Pacific Northwest National Laboratory, examining triple panes, including the thin triple insulated glass products that Ali was just talking to us about. Okay. Sorry.
No worries.
Worked out just fine when we were doing our practice,
Yeah.
but now I've lost my slides.
Oh no, no problem. Okay, there we go.
Right. we'll figure it out. Okay. So we all know that windows are a major source of thermal loads, and Lisa really covered this really well, but I just wanted to highlight here the fact that if we take a prototypical home and you build it to the IECC 2021 level, it's going to be making up about 7% of that envelope area, but it's going to be responsible for about half of those thermal losses. And so the bottom line is, if you want to make that leap in performance for your home or your building, you really need to improve that window performance as well. But the good news is we have lots of newer and emerging technologies in the market, including dynamic and electrochromic and thermochromic windows. Lance is going to be discussing those technologies later, as well as the vacuum insulated glass units. The most common commercially available advanced window products that are out in the market are the room side or fourth surface low E and the triple panes. And I'm going to be discussing the triple panes, including thin glass versions of the triple panes, some of the field validation work we did as well. So aerogels are also out there. They're shown on the right. This is a low density nanoporous structure that are composed mostly of air by volume, and they're very light, strong, highly insulating material, which hold a lot of promise. But to date, the clarity and cost of this material isn't quite to the level to make them commercially competitive in the US Windows market. So at PNNL, our research work focuses really on whole building integration, field validation. We work really closely with builder and contractor networks, both with our field validation and in support of the Building America Solutions Center and high performance builder programs. The field testing is designed to validate that performance for these advanced window technologies in terms of HVAC savings, grid system benefits, as well as non-energy benefits such as comfort and acoustics. And then we're also validating how this all plays out in the field. What does it take to manufacture, distribute, and install these window technologies in different regions and building types throughout the US? So we have two primary platforms, testing platforms that we use. On the left, I'm showing our PNNL matched lab homes. These are side-by-side homes matched in performance, where we use one as the control and one as the experimental, where we install whatever technology we're interested in. And then we have the ability to look at that performance at both the component level and then how it rolls up to the whole home level. And just a note, I was thinking that we have actually partnered with both of the manufacturers that are speaking and on this panel today, testing their triple panes in the lab homes. And so I can personally vouch that they have some great performance products. We also carry out field validation testing in occupied field sites throughout the US so that we can see the technology performs in different climate zones and varied baseline conditions, and also work with real life builders and home occupants to solicit their feedback and observations. So here I'm showing you a sample of some of the results from the lab homes testing that we did for thin triples. And the innovation with the thin triples that is pictured here at the top, Ali did a great job of explaining this, but the idea here is that we've had triple panes on the market for a long time, but the uptake has been very slow, somewhat minimal in the US. And some of the barriers that have been noted have been the higher cost, as well as the weight and the width. So the idea is we have an IGU that you develop that is slimmer and lighter with a thin, ultra thin glass, non-structural center pane, a foam spacer, gas fill. You can achieve that same triple pane performance, but you could potentially drop this into a standard lower cost double pane frame, manufacture at scale at a lower cost, so that you are working toward addressing that high first cost barrier, as well as dealing with some of the constructability issues that you might have with a thicker and heavier window. So on the left here, I'm showing the overall savings results of the side-by-side lab home test, as well as a graphical display of the daily heating savings with solar irradiation on the vertical axis and outdoor average temperatures on that horizontal axis. And, often we'll zero in on the bottom line, how much did it save on average, and which is 19% when compared to double pane clear glass in our control baseline home. So this is, maybe a likely retrofit application. And then the bigger bubbles that we have demonstrate that you get your highest savings on those cold and cloudy days in the winter. And one of the things that we could do with these field validation data, we have lots of great data, but we can kind of roll it up and disseminate it in a manner of different ways to reach different targets. And so I just kind of have a sampling of some of the reports and journal articles we might have, trade journals, and also technical reference manuals that are for the utilities, which love having sort of field validation in the region that they're interested in. We also work a lot with builders and contractors. They're a very important audience for field data, and P&L works closely with these networks to help with their decision making, whether it be case studies, design guidance, technical specs. And we also work with a new collaborative that I've mentioned right down there, the Partnership for Advanced Window Solutions. And I'll revisit some of these partnerships a little later. So we are able to successfully demonstrate the feasibility of dropping in the thin triple IGU and sorry, take a glass of water and choke myself. So the feasibility of dropping in the thin glass IGU into multiple frame configurations, multiple manufacturer frames. And this was done for both new build applications at the factory and glazed in as a retrofit. And another thing we always like to emphasize is that it's not always just how much you save on average, but when you save it. And window technologies, these high performance window technologies will save substantially during those peak periods when you really want to save. So on the left, I have the HVAC load profile during the heating winter season. And you'll see that the savings is primarily in those early morning hours. And if you're heating with like a heat pump, that's when you're going to be employing that auxiliary expensive heat. So that's a particularly important time to be, saving energy. Over on the right, you have the summer cooling season savings, and you'll see a substantial peak flattening. In fact, we had a 33% average peak electric load reduction during that cooling season, which is very substantial. And all those peak savings that you're going to achieve end up resulting in substantial thermal comfort benefits as well. When you reduce that temperature of the, increase the temperature of the glass in the winter season, that's going to not only impact that the comfort close by the window, but will reduce that effect, that draftiness effect, as well as produce even temperatures throughout the home. And those are noticeable comfort impacts. We also do some acoustic testing. The thin triple, one of the thoughts was that maybe it wouldn't provide as much acoustic benefits as, say, a regular triple, but we actually realized a 10 decibel reduction compared to the double pane clear glass that we had in our baseline home. And in the acoustic world, that's about reducing your the sound by half. Condensation is very important, and we see substantial benefits reducing the condensation potential on the interior surface of the glass. And the photo that I'm showing to the right is a home in Helena, Montana. This is a double pane low E window, so a code window up on the top that has actually ice buildup and condensation that's built up. It's a pretty high humidity home with, young children in this bedroom, but we were able to clear up all the condensation issues with higher performance than triple in this field site. So now I'm going to switch gears a little and talk about some of the work that we've done with high performance builders and surveys to assess sort of the factors influencing window purchasing decisions for some of these high performance builders. We surveyed 30 different builders, and we wanted to get a mix of builders who have opted to move toward triple panes and those that have not, and what were their reasons for going in that direction or not. And as you would suspect, it all comes out to how the benefits and the costs line up for these different builders. For the builders who opted to move toward triple panes, they noted that performance, being able to easily meet high performance specs was a #1 reason for moving there, as well as flexibility in design. And Lisa mentioned this, that you are able to downsize that HVAC, but a lot of the builders we worked with said that just being able to be flexible with your design, maybe have shorter throws, duct throws where you want them to be, being able to use mini splits, was a definite benefit from the higher performance windows. And then there's also what they noted as very marketable benefits of comfort and acoustics and condensation reduction on those windows. The primary reasons for not moving toward triple panes was what we would suspect would be the material costs. And what we want to kind of make the point here is that you will see a substantial price range for windows across all performance levels. Lisa, again, made this point pretty well. But when Energy Star EPA was looking toward upping their specs for windows, they did some consumer price research. And the truth of the matter is, yes, there is a cost premium for the high performance windows, but it's not necessarily the energy saving features that are driving that cost. And on average, moving toward for like frames, moving up is going to add about $100 per window. But you might have to shop around to find these products. The second and third reasons that some of these builders did not move toward the higher performance windows, triple panes, was these search costs, just not being able to get products, spec them, and get them to the site when they need them. And the other reason was the fact that Energy Star at the time did not require triple panes in their climate zone. This has now changed. The version 7 of when Energy Star is out, all those highlighted numbers there are specs that have changed since the version 6. And so now it really is the case that you could have a surface floor low E, or a triple pane is what you're going to need in the northern climate zones. So what we have done then at the NFRC and the Efficient Window Collaborative and Energy Star are working toward trying to make it easier to find these products with some window finding and selection tools. And we at the Partnership for Advanced Window Solutions, PAWS, are also trying to gather information to help with this search and acquisition costs. And speaking of PAWS, one of the activities that we did is host a window manufacturer and builder meetup at the EBA High Performance Builder Summit in 2024. This was a great summit where builders were able to kind of articulate where their pain points are for windows, and what is helpful, the benefits that they're seeing with some of these higher performance windows as well. And just as with the survey that we had before, they pointed out that it's not just simple costs. It's certainly material cost is a big factor, but it's also a little bit more nuanced. Some of these hidden costs, being able to spec what you want and get what you want. And then, of course, all the benefits noted were in line also with the condensation resistance, being able to have good quality air leakage, durable over time. They don't want any callbacks. Moisture control and sound insulation are all marketable benefits. So if you were wondering how you might in the builder community help pull this market for high performance windows, I do have some ideas. This is something that if you're in that builder community, we really can strengthen that demand signal by specifying more high performance windows, working with a window dealer near you to spec out these higher performance options, request higher performance options, and upsell your clients with better windows and window attachments. I haven't really gotten into that today, but the shades and automation rated by the Attachments Energy Rating Council, also another way to improve the performance of your window. Engage in any workshops, and I'm happy to report that we will be hosting another window manufacturer builder meetup at this year's EBA in a few weeks in St. Paul, Minnesota. And so please feel free to reach out, and thanks for listening, and feel free to reach out to provide any input you might have on this topic. We're always looking to engage. Thanks.
Thanks a million, Katie. Love the real world savings, and especially that bubble chart you had was so great to see. So yeah, thanks a ton. And I think there's some more questions in the chat, and we'll hit those right after Lance goes. So Lance, definitely last but not least, I'll let you present, and then we'll hit some Q&A.
Excellent. If you could stop sharing, then I can share mine. It's not allowing me to do it until you've stopped sharing.
I did it. There we go.
Perfect.
Great, thanks.
Looking for that button.
All right. So I have the pleasure of batting cleanup today. And
Yeah.
hopefully it'll be a little more forward-looking. All right, how are we looking?
Good. Just need to go into presentation mode. I think I see you in a I think presenter view. I'm seeing your like next slide thing, so it's not quite full screen.
All right.
Maybe just exit out and then go back to present. You might be in the Zoom presenter mode as opposed to the like PowerPoint.
How's that? I've swapped it.
Yep, perfect. Okay, looks great now.
All right.
Killer.
Get into it. Cool. Yeah, my name's Lance Wheeler. I'm a research scientist at the National Renewable Energy Lab, a sister lab to PNL you just heard from. I've been at NREL for about 11 years working on material science, and my current title is the group manager for materials physics. I won't be talking a lot about physics today, but I will be going through an overview of what I would envision as sort of next generation windows and focusing a lot on photovoltaic windows. So we're not only focusing on thermal heat mitigation, but also looking into how you can generate electricity in your windows. So I would say there's about three main areas of innovation in Windows, and you heard a lot about number one, increasing insulation. You heard a lot about triple pane windows. There are actually other avenues of increasing insulation that I'll touch on very briefly. Secondarily, there's dynamic and chromogenic materials. There's chromogenic windows, which includes things like reversible electroplating you see on the bottom, and a mechanism that actually behaves a lot like a battery up top, so electrochemical tinting. And then on the right side, this third generation or this third idea of innovation is where you're actually using your windows for photovoltaic energy generation. So I'll cover the mostly topic 3, but I will touch on 1 and 2 very quickly. So we've heard most of the presentations today have focused on basically going from the left of this chart towards the right of this chart. And so on the left side, you've got what is the current standard, a double pane low E glass window where you have an R value of usually around 2. And as you go to the right, we've heard about triples and definitely a lot about thin triples. You can get up to an R value of up to 5. Emerging areas include aerogels, and aerogels, you can imagine the pink insulation you have in your walls. An aerogel is basically trying to make a similar type of material, but making it transparent. So there's lots of challenges that go along with that. But that will provide R values of predicted up to something like R15. And I will spend at least one more slide on VIG, so vacuum insulated glazing, where we're basically changing the paradigm of how we're insulating. We're no longer using gas fills or things that prevent transport in that gas layer or prevent radiation from these layers from low emissivity coatings. You're actually evacuating 2 panes of glass, and you're holding a vacuum between those things, which allows for a much, much higher thermal insulation. And so there's actually a lot of action in this currently. And the dream of all this is that can you get to the point where your window has the same R value as your wall? So you're aiming for at least an R value of something like R30 or more. There are products out there right now that are getting close to R20 for vacuum insulating glazing. Before I wrap up VIG, I just want to say that, like I said, there's a lot of momentum on this, but it's not really a new idea. It's something that was predicted or at least proposed in the early 1900s. There's been a product that was on the market in the late 90s from NSG Pilkington. It was mostly sold in Japan. But right now you see a lot of action in the US. And so this is just an array of different headlines that I've grabbed looking at startup companies like Lexwall and very established window manufacturers in the United States like Vitro, Guardian, Velux, big companies like Panasonic. And then on the bottom right, I'm showing, Bill Gates is actually backing VIG companies. And so VIG has a lot of momentum. It's because of that offer for higher thermal insulation, higher R value. Something that hasn't been touched on very much, but at least just glossed over, is the idea of dynamic glazing. This is also a commercial technology, something you could buy right now from a number of different vendors. Sage Electrochromics has been around for a very long time and is probably the main player there. They're bought by Saint-Gobain, which is a French company. On the left here, I'm showing actually as an example the Dreamliner. That's where I think a lot of people come across these things. The windows in the Dreamliner actually have an electrochromic organic material. So you change the dial, its voltage-driven change in your transmission. So you're seeing tinting as a function of just applied voltage and time. And so these are, like I said, they're on the market. Part of the problem with deployment in these is that you actually have wires coming on your windows. So now you have to employ not only a glazer, but an electrician to install these things. And that's actually a common problem when it comes to photovoltaic windows I'll get into later. On the right side, it's another type of dynamic window or chromogenic window. It's a passive technology. And actually, that's why there's been lots of adoption and some success here. There's a company in Michigan called Pleotint that has manufactured these things and sold them commercially, where you're using temperature to drive the change in tint. And so there's chemistry that happens between 2 panes of glass. It's basically an interlayer between 2 pieces of glass, like a laminated glass that will then change color. And I will show some variations of this where we're actually getting the photovoltaic effect out of it later. So I wanted to show those because they haven't been touched on a lot, but I will spend the rest of this time talking about photovoltaics and how they can be incorporated into windows. When it comes to window technology, I think, as technologists, scientists, researchers, we've been thinking a lot about how to make windows better. And of course, driving thermal efficiency has been really the name of the game for a very long time. And so thinking about, new ways to save energy in your building is interesting. And I think energy generation is one way that we can go. I think one of the more promising ways to go. Let me just dig a little bit into just PV in general, and I'll compare them to windows. The left side is showing just a typical PV laminate, and the way you might find them right now in the marketplace. The interesting thing here is most of the mass, especially when it comes to thin film technologies, goes into the glass. And so the majority of the mass and the cost, it turns out, of a panel is the glass itself. Now, if you're talking about just swapping out a PV panel for your window, it should make a lot of sense if that's true. Of course, there's more to it than that. And actually, a little bit was talked about when it comes to soft costs, things like integration and planning and customization. All these things add to why these things aren't in your windows now. But they do speak to the promise of PV windows because they can really piggyback costs, especially materials costs, of what's already going to be in your building anyway. So the right side here is actually just showing this for a next generation technology, but the numbers that are associated with, say, glass and the other components should be accurate. So the red ones are the ones that are shared with the glass laminate. So the left bar, the middle bar is your front and back glass. There's a transparent conductor on there, which is needed for PV, but it's also what you find in the low emissivity coating. So it's a piggybacked cost. And then the asterisk here is the green bar on the right, where the balance system makes things really difficult. Not only for typical PV deployments, that actually adds a lot to it, but especially in BIPV or PV windows, where you have to make custom sizes, you need to then build the balance systems into the building. That's a big challenge when it comes to PV windows. So a snapshot in time, well, actually over a long period of time, for the efficiency of PV and different technologies. And this is kind of a busy slide, so I'll go through it fairly slowly. But this is a famous chart by NREL. You can find the most up-to-date one on NREL's website. It is efficiency, and so that is the power of the sun over the amount of power electricity that you get out of your solar panel as a function of time. Actually, I'm showing cells, so the individual cells that compose a module. And the blue line here is single crystalline silicon. And so something like 99% of all utility scale solar, like you drive by a big solar array, that is probably going to be silicon. 99% of it is silicon, or 60% of it is silicon. Stuff on the rooftops is 99% silicon. The other 40-ish% that's out in utility scale is from cadmium telluride. You've maybe heard of First Solar as a company. It's one of the only US-based manufacturers of solar that's still around. They make thin film technologies, which has its own benefits, and I'll talk to them or talk about the benefits as a function of window in a second here. But that is basically what composes the entire market. It's the blue line and the green line, and when it comes to residential rooftop solar, it's entirely the blue line. So there's lots of interesting things happening in the research area for these different technologies, for these different solar technologies. So perovskite, an area that I work in. They are actually just as efficient as solar or silicon right now. They just need to be made more durable. And actually, if you put it on top of silicon, this perovskite technology, you can then get a 35% efficient technology, which is much better than what you can currently get in the market. Again, its durability is a challenge there. Organic photovoltaics has seen a big rise in efficiency in the last 10 years, up to about 20%. And that is not the transparent form of it. But the reason why OPV, organic photovoltaics, is very exciting for windows is that you can tailor how they absorb, which makes them an ideal candidate for thinking about windows and actually BIPV of all different kinds. The other one I put in here is amorphous silicon. It's down here at 14% on the right side here, and in 2025. It really hasn't been worked on very much, but when it comes to commercially available PV windows, you really have two technologies. There's single crystalline silicon, in which you can then cut up these opaque wafers into interesting shapes. This is just showing lines in the upper right here, the segmented version of it, to make windows. And this is a product from Vitro. And then the other option is where you take the absorber material of a photovoltaic, you put two transparent metals on it, and then you thin down the absorber so thin you can see through it. That gives you a much better aesthetic when it comes to windows. And I have an example of this from Onyx Solar on the bottom. But currently, the only thing that's market available is amorphous silicon. And the thing that you see in this picture down here, we can see there's a lot of light transmission. It's something like 2 to 4% efficient. So you take a big efficiency hit when you make amorphous silicon thin. And this is a big complaint about PV windows. It's like, well, why don't I just put these things on my rooftop? And my answer is almost always, well, if you're out of rooftop space, where are you going to go? And if you want a more efficient window, let's think about PV generation as a system whole for the window. So if you're not only preventing heat in and out, you're also generating electricity. It adds to that system and makes it more efficient. And then one more note on efficiency. The segmented version I show in the upper right here from the Vitro, these slots of single crystalline silicon. If that is a 22% efficient module when it is fully opaque, you can literally take away the extra area that you're letting light through and take that away from the efficiency. So if it's 50% visible transmittance and 50% solar area, you're at 11%. So the math is that simple. So there are more ways to do this. The ones I just described are on the left, which is a fully opaque PV. And actually, I will note really quickly here, I add a lot of blue bars down here. So for future reference and look up some of these resources that I've been pointing out, these are all very useful. And yeah, Richard Lunt and his group have done a lot of work towards PV windows. So left side here is opaque PV. The boxed ones are the ones I just described, where you have segmented PV, where you basically take your PV cells and spread them apart. They're fully opaque, but they're spread out and let light through. You can thin down a colored absorber, an absorber that actually absorbs visible light, as most absorbers do. The other strategies are here on the right. I think these are ones I won't get into very much, but I think they are very exciting. I will talk about the organic photovoltaics in a second here, but you have the ability to take a layer on your glass, absorb some of the light, and then redirect that light to the edge of the glass, then convert it on the edge of the glass. You can have all of your electronics on the side. The beauty of that is you don't really see any wires. You don't see any electronics. It's all hidden in the frame of the glass. And so this idea of solar luminescent concentration, which I show in the middle here, there's both a colored version and a transparent version you can make. The problem with these is they're very low efficiency, but they are sort of a next generation technology. And there are startup companies and certainly lots of academia and academics and national lab researchers working on this kind of thing. The thing I will dig more into is this second from the right, and this is organic photovoltaics. This is where you're actually selecting how the photovoltaic absorbs, and you basically avoid absorbing visible, which you can't do with typical materials, but you can with organics. It allows you to make fully transparent materials where you can actually convert, infrared and UV as opposed to visible and actually get high performance. So this is highlighting some work from NREL. The reason why OPV is attractive for Windows is because you can make the materials not absorptive in the visible, so basically selective absorption in the near infrared and UV. You can use this for glazing for windows, and actually we have a whole project now where we're doing this for improved plant growth, and so you can tailor how these things absorb. So then you let the light through that the plant wants, and you actually can make both better plant growth and you can allow energy generation in a meaningful way. So I'm using this as like an example of not only can you make it transparent for the way people typically want their windows, you can also tailor it to be basically any color and tailor it to whatever's behind it. So if you wanted a yellow window, you could have a yellow window. If you wanted a blue window, you could have a blue window. And you have trade-offs when it comes to efficiency, but it is a really cool technology in the sense that you can fully tailor it for whatever sort of need you have. And so I've avoided talking about my own work this whole time. But I will show this movie. This is my own work from about 7 years ago, where we're taking this chromic effect. I mentioned electrochromics and thermochromics, and we're combining it with the photovoltaic effect. So this is taking perovskite, a material that's this sort of next generation, highly promising technology, and we can bleach it in the lab. And so what you're looking at is 2 panes of glass, and in between the pane of glass, one of them has a coating of perovskite on it. We bleach it with a gas, and then as a function of temperature, you will then expel that gas molecule and tint back into this darkened state. And so now you've basically, for the first time, combined a thermochromic or chromogenic effect or changing color effect with energy generation. And so now you can actually imagine that the hardest part about this experiment that I'm showing you here is finding an incandescent light bulb. So we're basically just taking the incandescent light bulb to heat up the film. It gets to something like 60 C. And so I'll speed it up here in a second, but you'll see as a function of time when it cools down, that darkened spot, that ring goes back to this clear state. And so again, we've combined thermochromism with the photovoltaic effect. And the beauty of that is not only you're mitigating solar heat gain like you would with an electrochromic or thermochromic, you're also in this very darkened state. And so you should be able to get to very high efficiencies. Efficiencies you can't get to if you have that semi-transparent like the current technology. So this is very quickly just some modeling that we did, and it's looking at the different types of windows on the left side here. And so the left axis is energy use reduction. This is a typical building in Denver. If you go from double pane to double pane code, where you basically put a low emissivity layer, the low emissivity layer does a dramatic reduction in your energy usage. And going to triple also improves energy usage, but it's not as dramatic. And then taking those 2 different technologies, the code and the triple, and adding dynamic technologies to it, it adds comfort, but actually your energy reduction is fairly small. But if you compare that on the right side here, where I have the power conversion efficiency, PCE, on the x-axis, again, looking at how energy use reduction is impacted by power conversion efficiency. The different technologies I just talked about are all these different arrows, these different markers, and as a function of power conversion efficiency, your energy use reduction goes down dramatically. And again, this is thinking about the system as a whole, not giving this back to the grid and that kind of thing. But if you can get to a 20% efficient photovoltaic window, and again, that's pretty far out there. This is sort of looking into the future. You could look at a 2-fold reduction in what we can currently do with triple pane windows. And that is especially true if you can do it while switching. So that dynamic effect, which mitigates solar heat gain, and also gets to this very dark state, so you can convert a lot of photons in the visible. So that's all I wanted to show as sort of an overview for photovoltaic windows. And I know it was just a quick snapshot. I talked a little bit about next generation for thermal energy management and chromogenics in general. The last thing I'll touch on is we got involved in a project with the Architectural Solar Association, where the goal is just to educate the marketplace. And so we have a YouTube channel with different sort of educational videos. There's also a class we have online. If you go to ASA's website, And this has been supported by lots and lots of industrial partners. And so I wanted to point that out. If you're looking for more information on not just PV windows, but integrating photovoltaics in a meaningful way into the construction and building, or in the construction process in the eventual building, this is a great resource, and I wanted to advertise that. And besides that, I'd be happy to, take windows on, or take questions on PV windows, PV, or anything in between.
Awesome. Thanks a ton, Lance. That was such a great forward look, and really exciting to see these new technologies in the market. And I'm sure for many, including myself, I hadn't even heard of some of the potential options that are out there. So again, super, super exciting. And thanks again. Well, huge thanks to all our presenters today. We do have a few questions in the chat, so I'll just call out some of those and have folks answer. I know there were a couple already answered in the chat, but just so folks can kind of get an idea of some of them too. We have a question for Ali. Did he show a thin triple, and which windserts that you showed use the thin glass?
Sorry, I only caught the second part of that question. So all windsert products use the thin glass. So the Windsert Light is a single sheet of thin glass, and then the Windsert Plus is a double pane unit. So one piece of thin glass and one piece of conventional glass, either 1/8 inch or 3/16 thick. And then what was the first question?
Yeah. Oh, did you show a thin triple, which I think you did, right?
Yes, I can beam that back up.
Perfect.
So this guy here, let's see if we can blow him up. There we go. There's a thin triple. I think I've got
I'm not
another
seeing
one.
your screen.
Oh, okay. This guy. Share. So that is a rendered one, and then here. Oh, there we
Perfect.
go. Yes,
Yeah,
there's
so
a thin
cool.
triple.
Amazing. Great, thank you. Yeah, and then Ali, there were another couple questions directed at you. Does the Windsert preserve window operability?
It does not. No, it is fundamentally designed to go behind a fixed window. So we've been experimenting and with some operability, some hinging on the side, or maybe it's more like a Bermuda shutter that you could lift up. But right now, the core product is just for a fixed insert.
Cool. And then last one here. Someone said, you mentioned condensation improvement over previous single glaze. Does this require ventilation of that new air pocket, or is there a desiccant component?
A lot of discussion has been had about this, and we've done quite a bit of modeling and real world studies, and it's really hard to predict when that condensation may appear in between the two panes. There's sort of a sweet spot between having a very leaky window. It's almost as if you have a very leaky existing window, then you're sort of flushing that cavity all the time with colder air, and we never have that warm, moist indoor air cross over and form condensation. But we've had some, kind of freak weather patterns where all of a sudden certain windows did form that condensation in between the panes. So there's not a really great science to predict when it's going to come. We have been experimenting with desiccants in between, but we've not employed that yet. So right now, if that condensation does appear, typically it will disappear within an hour or two as the space warms up again. But if it leads to any sort of fogging or anything, the Windsor can be easily taken out, cleaned up, and put back in. And so the occasions where we have seen it, it's been very short lasting and only on a few days of the year. So we haven't found the need to really develop that desiccant solution for those brief events.
Got it. Thanks so much. And question for Lisa here. I know you did type an answer in the chat, but I think this is just a great point to go into a bit more. So the question was, did you do a cost comparison to look at what premium for upgrading to triple pane is, and also taking into account savings from downsizing mechanical systems? And Lisa, you were saying that it'll often pay for itself, just reducing the size of the air source heat pump, but I was hoping to get a little elaboration there. I think you're on mute.
Sorry. Yeah, you're correct. It depends on the market, the size of the house, the actual tonnage that's reduced, but we're talking we were looking at a 3,200 square foot house that had 1.5 ton reduction, and it in the Northeast anyways, the savings was about between $500 and $600 a half ton. So that amply paid for the upgrade on the windows to go to a tri-pane. And then, and there was also a question also asking about whether or not we did it on multifamily. And so part of our initial study was on townhomes. So it wasn't like a true multi, 4 or 5 story, but we did do townhomes. So yeah, it really depends on what part of the country you're in as well. But and so but in zone 5, like I said, on a 3,200 square foot home, we were 1.5 tons, and it amply paid for the upcharge. So obviously, there was someone asking also about the ROI. On a new build, it's pretty easy because you already have to have windows, right?
Yeah.
So you're already putting in windows, so it's a much easier sell than when you're doing a renovation. So obviously, it's a different animal.
Yeah, great point. It sounds like in a renovation too, if you're renovating your house to include a heat pump, say going away from a gas system, right? Heat pumps are often quite expensive and they're very related to how many, for a mini split system, it's how many heads do you need, and then of course the BTU output. So it sounds like maybe upgrading your windows in that retrofit situation could be useful too.
Yeah.
Just get away with a smaller system, right? Like people always talk about a passive house, right? Where you have a very few very little airflow going through the house, low air exchange, right? And those type of houses are able to have incredibly small HVAC systems. So it seems like this could be a similar deal. Great. So I think most
And Nancy asked a very good question. Why do they sell mainly sliding windows in the west and east and double hung in the east? I tried a couple times that attempt to I think it's just people came, in the east, people came over from England, and they're mainly a hung market, and it just kind of carried on. That's the only reason. Where I'm at in Quebec, where it's French, we have a lot of French casements and casement windows. So as odd as that, I think it depends on who emigrated there first.
Yeah, fascinating, interesting. So I didn't even know there was a historical component there, but clearly that's affected the architecture, affected the window design. Super, super
Yeah,
cool.
exactly.
Awesome. I'm just looking through here to see if we have anything else open. Someone had a question for Lance here. On your third slide, is the unmarked exterior to the left and the interior on the right? Maybe Lance, do you want to pull up your third slide so we can get some context there?
Yeah, I'll pull it up. The short answer is yes. So that's a surface 2 low E, and the outside would be on the left side here, interior on the right side.
Very cool. And while we're here, right, talking about R values, a couple people asked about thermal bridging, and I don't know if that was talked about too much during these presentations, but if anyone wants to go into thermal bridging and kind of how that works with Windows and how maybe some of these innovations could help with that, if anyone wants to answer, that would be awesome.
Somebody more versed in frames than myself, probably.
Well, I mean, we're talking about when we talk about certainly when the industry, and I think, you know, Ali will concur, we talk about whole product U value, not center of glass. So we're not talking about, and I think that most of the modeling, I know Ivan asked the question, and I sent him my email and asked him to, I will get back to him on our particular study. But I think that the most energy modeling right now does take into consideration thermal bridging. So I can't answer. Certainly when we talk about U values, we talk about whole product U values. Some of the design work that we've done was exactly to try to minimize how we were able to get a 0.14 window was to minimize the thermal bridging from the exterior glass to the interior. And so that was a major accomplishment that we had to try to do. So yes, it's already incorporated, if you will, in the whole product. But as far as I think Ivan's question was, you know, were we calculating the insulation around the window and the, you know, between the window and the stud? And so I didn't have an answer for that yet, but I will get back to him on that.
Awesome.
I think it's a good point,
Sorry,
though,
go
because
ahead.
especially on this slide in particular, we're advertising center glass R values. And so if you're thinking about insulating your building, you need to take into account the entire thing. And so R20 is something that vague people like to brag about, but it is a problem because as soon as you get to the edge, your R value goes significantly down.
And that's why when you're using VIGs, you essentially, in order to counter that, you have to put it into a hybrid system. Mostly, what I've seen, anyways, is you have to put it in a hybrid system, and especially in places where you have extreme temperatures, so more northern places. But yeah, it's thermal bridging is a large question.
Absolutely.
And-
Great. Well, any closing thoughts here, folks? We're almost at time. But if anyone has any other comments they want to make based on questions they've seen, you can totally go for it.
Could I share one slide or one screen real quick?
Of course, yeah.
Total kind of nerding out on this idea of thermal bridging and frame design.
Yeah, totally. Love it.
I've known for a long time that the European model, they improve their frame performance by making the glass pocket bigger. And it finally became clear to me when I was actually modeling a hybrid VIG versus a thin glass quad. And what I'll draw your attention to is the blue kind of rainbow pattern here within the frame. So same frame, just changing the glass and the overall thickness. So although our thin glass quad has a center of glass U factor 0.10, the whole window U factor ends up being 0.17. And that's because we're moving out that the short circuit of heat loss. So we're expanding that thermal bridge. So our thin glass quad glass is worse than the VIG, which is a 0.043. But because of that, thermal bridging that's happening, we're ending up with the exact same whole window U factor. And so just by virtue of making this pocket bigger, we extend the amount of time it takes for that heat loss to happen. So we lengthen that thermal bridge, I guess, for lack of a better word, and we can achieve the exact same whole window results. So seeing this is sort of one of those light bulbs, like, I get it now. It totally makes sense. So it was kind of exciting to discuss, and kind of keeping in mind, like, we've got all these cool, thin glass technology where we're fitting it into narrower spaces, but we are always going to be a little bit hamstrung by the fact that we're trying to go narrow, whereas just making things a bit wider, we can pick up more performance.
Cool. That's such a nice point. Awesome. And that's a great note to end on too. Just, clearly that small details like these can have a huge impact, but Yeah, well, Lance, Lisa, Ali, Katie, thanks a ton again for being on. This was great. Super interesting content. If folks have questions, I think they have contact addresses to follow up. Again, like Shannon mentioned earlier, this will be recorded, so you'll be able to go back and catch anything you might have missed or share the content. But yeah, with that, thanks again, everyone. Thanks for being on. Thanks to our presenters, and have a lovely rest of your day.
Thank you.
Thank you.
Cheers.
Cheers.